When a rigid body moves in rotational motion, we know that all of its pieces are moving, and that means that they possess some kinetic energy. Since all of the pieces have the same angular velocity, though, we can actually write this kinetic energy in a very simple way. It's equal to 1/2 times the moment of inertia times the angular velocity squared. All of the difficult aspects of different pieces of the object moving in different directions with different speeds are combined into the single factor for the moment of inertia. So if we know how to calculate the moment of inertia for that shape, we can just plug in that number to this slot. If our system consists of multiple objects, which might be rotating, translating, or both, then this kinetic energy is just one piece that gets dumped into the sum of the total kinetic energies. Notice that this has a very familiar form, 1/2 times a mass factor, here it's moment of inertia, times a velocity factor squared, here it's angular velocity. We'll see this pattern repeats when we look at other formulas for rotational motion. They look just like the formulas for linear motion, but instead the variables are replaced with their angular versions. There are two places where we'll see this in problems and have it be useful. The first one is where we have an object that can rotate about some axle, and it's attached to some other objects or external forces through a string that has some tension. I'll label the force of tension on the string as T, and the radius of the object as R. There are two properties of this situation that we can write down. The first one is that the tension force if it comes from a string which is wrapped around the circumference of the rotating object, if it's wrapped around, then the tension is always in a tangential direction. So T is directed tangentially. And you can try this out, wrap a string around a cylinder and pull on it. From any way you pull, it's always going to adjust itself to be pulling tangentially. Until the string is totally unwound, it's not going to be able to pull in any other direction. The second thing we can say about this is based on the constraint of a string having constant length. If a location on the string, imagine we taped a little flag to this spot or something. If that location moves due to the string being pulled some distance, let's call the distance delta x, then that means that every other point on the string must move the same distance. So this point, this point, this point, they must all move the same distance delta x. For a point on the string where it's wrapped around, to move a distance delta x implies that the object is rotating through some angle, delta theta. Of course, on the circle, angles and distances along arcs are related by the radius. So delta x is equal to r times delta theta. This means in this situation where a string pulls tangentially and makes an object rotate, there is a direct relationship between the distance that the string moves, or objects attached to the string move, and the amount that the rotating object rotates. We can write this in another way if we consider the rotations to be done over time. Right now it's all in terms of magnitudes. Delta x, delta theta are both considered positive. But to get the right sign on these quantities, let's remember that a positive angular velocity is a counterclockwise rotation. And a positive displacement would be a motion to the right. So it's clear that if we pull the string to the right, the rotating object must actually rotate clockwise. Therefore, we have a situation where the linear velocity must be equal to the opposite of the radius times the angular velocity. Now notice that this looks kind of bizarre because we were saying in previous videos that V equals positive omega r. And what we were talking about there is a situation where something is rotating in the positive direction, and we just talk about its speed, independent of what direction it's moving. But here, our symbols for V and omega mean a little bit different. V is the velocity of a point on the string or something attached to the string. And omega is the rotational velocity of the rotating object. The second situation where we'll see this rotational kinetic energy become useful is when an object is rolling along the ground or along some surface. When an object rolls along a surface, its center of mass is moving, and it's rotating at the same time. It has to do both of these motions in order for the point of contact to not slip. If the point of contact is not slipping, then we call this a static rolling situation, or rolling without slipping. If the object could roll and slip, there would be no need for the angular rotation to match up in any way with the velocity. Imagine a ball on an ice surface just kind of sliding along. It doesn't need to be rotating at all to just slide side to side. Right? Also, we could imagine some sort of wheel skidding, maybe on a car with a slick road. The wheel can rotate rapidly, but if it's slipping on the ground, the car can stay in the same spot. So these two quantities, omega and VCM, will only be related if we have the static rolling condition. Let's think about what that condition is. For static contact to be maintained at this point, the velocity of the surfaces touching each other must be the same. Generally, we think of the surface below, or the ground, to be at velocity 0. That's our frame of reference. But the velocity of the rolling object is composed of two parts. Let's call the velocity at the bottom here, if it exists, v sub a. We'll call this point A. If the object was moving side to side without spinning, there would be a contribution VCM. All parts of the rolling object would move at the same velocity. If the object was at rest and rotating with an angular velocity omega, there would be a contribution omega times r, where r is the radius of this rolling object. So when both things are happening at the same time, both pieces contribute to the velocity of a bit of mass at location A. Now, for order there to be static contact, the velocity of a bit of mass at point A in the rolling object must be 0. And that means we have a 0 over here. And so the velocity of the center of mass and the velocity, the angular velocity, are linked by this relationship. Now this looks a lot like what we have over here, again, but remember that these V's and these omegas are interpreted possibly differently. Here, this omega is the rotational velocity, with positive considered counterclockwise. And here, VCM is the velocity of the translational motion, the center of mass moving wholesale to the left or to the right. Let's set up some example problems where we use conservation of energy along with these two basically constraint situations to solve a problem involving some rotational motion. First, let's set up something rather simple just to see how the numbers work together. Let's take a cylinder. Axle at the center. So it can't move. it can only rotate. I'm going to specify the mass of this cylinder, 20 kilograms. The radius of this cylinder, 8 centimeters. And I'm going to specify that there's a force applied to this cylinder at the left by a string which is wrapped around the outside of the cylinder at a radius r. That force has a magnitude of 50 newtons. So that's the situation. Now the question is, if the cylinder begins at rest and the string is pulled for 5 revolutions, what is the angular velocity omega of the cylinder? Okay, so we'll be able to solve this by using conservation of energy. In this situation, we don't have any potential energy, we only have kinetic energy, and we only have one type of kinetic energy. We do have an external force which will do some work on the system. So our starting point for equations is the work-energy theorem. Work is equated to the change in kinetic energy of the system. To find our work, we need to think about the force and the distance through which it pulls. If we pull and the cylinder rotates 5 total times, then a point on the string or a point on the outside of the cylinder would move 5 times the circumference of the cylinder. So our delta x in this case is 5 times 2 pi r. That's 5 times the circumference of the cylinder. If we plug in a radius of 8 centimeters, this comes out to 2.513 meters. That displacement is the displacement of a point on the string. If the string is pulled out, that displacement would be in the downwards direction, parallel to the force. So for calculating this work, I'm allowed to simply multiply this force by the displacement because they're in the same direction. So W, work, will be the 50 Newton force multiplied by the 2.513 meter displacement. That gives me a work of 125.66 joules. There's no rotational motion yet, except for what we know about the string. For the rotational motion, we'll be looking at this kinetic energy term. The change in kinetic energy is the final kinetic energy minus the initial. And the final kinetic energy is 1/2 the moment of inertia times the final velocity squared. The initial kinetic energy is simply 0 because it begins from rest. So we are now going to use the work energy theorem and equate our 125 joules to 1/2 times the moment of inertia, which I'll write in a moment, times the final angular velocity squared. Now for the moment of inertia, we need to think about what type of object is rotating. Here it's a cylinder. We know its mass and its radius. So we know that the moment of inertia of a cylinder from the table of moment of inertia formulas is 1/2 times its mass times its radius squared. So the equation has 2 factors of 1/2 in it. One for the kinetic energy formula itself, and one coming from the shape of the object. These are different, and they both belong there. So if we plug in our mass, 20 kilograms, our radius, 8 centimeters, to this formula and solve for the final angular velocity, we will get 62.66 radians per second. That's about 10 revolutions per second. Let's look at a different type of problem. The next problem is going to involve the constraint of rolling without slipping. This problem is a classic in the study of rotational motion because it has a very non-intuitive answer. I'm going to set this up as a general formula exercise, a derivation, so we can solve the problem once and for all without looking at specific numbers. What we're going to consider is an object that rolls on a surface at a radius r. The object has a mass symbolized by m and a moment of inertia symbolized by I. The moment of inertia will depend on the mass and the radius, but we don't know the exact formula because we are not going to specify the shape of this object. The object begins from rest at a height y equals h. And ends at a height of y equals 0. So it descends through a distance h. And the objective of this derivation is to get a formula to predict the final velocity of any such rolling object. So our approach to this will be based off of the constraint of rolling without slipping and conservation of energy. Let's write out the formula for the energy before and the energy in the final situation. We have a contribution to kinetic energy from motion, kinetic energy from rotation, and potential energy from its vertical position. Since the initial situation has the object begin from rest, we know that this term is 0, and this term is also 0. At rest means it's not moving, and it's not rotating either. So our total initial energy is simply mgh. Now let's write out the expression for the total energy in the final situation. We again have kinetic energy due to translation, a kinetic energy due to rotation, and actually 0 potential energy because we're at height of y equals 0. So our formula for total energy in the final state can be simplified somewhat. At first, we'll write this as 1/2 times m vf squared plus 1/2 times moment of inertia. And now we will use the constraint of rolling without slipping. For this object to roll without slipping, we know that the final velocity must be equal to minus the angular velocity at the final situation multiplied by the radius of the object. So here, since we have omega f, we will plug in minus vf over r squared. This reduces the complexity of our equation because now it only depends on the final linear velocity. We can simplify this one more time. I'll move up here. I'll rewrite E0 as mgh, and I'll rewrite EF. We'll have 1/2 times the quantity m plus moment of inertia divided by radius squared times the final linear velocity squared. These two energies should be equal due to conservation of energy. There's no friction in this situation, even if the surface has a static friction, because when something rolls without slipping, there's no way for that frictional force to do any work. So our equation of conservation of energy is mgh equals 1/2 times the quantity m plus I over r squared times vf squared. My next goal is just to solve this for vf. When I do that, I'm going to get gh times 2 divided by 1 plus the moment of inertia divided by the quantity mr squared. That entire expression must be calculated and then a square root taken to get the final velocity. I've arranged this algebraically so that all of the terms involving the moment of inertia are grouped together, and I've done this for a specific reason. This equation actually is kind of interesting. The final velocity is the square root of 2gh divided by something that's unitless, right? Moment of inertia is usually expressed as mass times radius squared times some fraction or something. So there's a couple of cases that we consider to get a feeling for what this prediction means. If the moment of inertia was taken to be 0, the object was not allowed to rotate at all, say, and slid completely frictionlessly down the hill, then our answer would be Vf equals the square root of 2gh. This is the same exact answer we would get for an object just sliding down a hill without friction. So our derivation here is consistent with that previous simpler answer. But the more interesting part about this is how the moment of inertia actually appears. We take our moment of inertia and we divide it by mr squared. Remember, for most rolling objects, the moment of inertia is equal to some fraction times mr squared. So this final velocity doesn't actually depend on the mass of the object. In any case, the moment of inertia will be proportional to the mass, so the mass will be canceled. It also does not depend on the radius of the object. The moment of inertia will depend on the radius of the object squared, so that cancels out. So the only thing this final velocity depends on for the object is its distribution of mass. What shape is it actually? If we use the formula for moment of inertia of a cylinder, 1/2 mr squared, then our final velocity will be the square root of 2gh divided by 1 plus 1/2, so 3/2. We can simplify that a little bit to be 2 times 2 in the numerator, so 4/3. 4/3 is less than 2. We've got a 2 here for sliding and a 4/3 for rolling. So a cylinder rolling down this hill actually ends up going slower than an object that just slides. And that can be understood easily by some of that initial potential energy being taken up by rotation instead of just sliding motion. Let's consider one more case. A favorite object to roll down hills is balls. Let's take this to be a hollow ball, like most sports balls. In that case, the moment of inertia is 2/3 mr squared. So there we would get a final velocity of the square root of 2gh divided by 1 plus 2/3. 1 plus 2/3 is 5/3. So if we simplified that, we would actually get a final velocity of 6gh over 5 under the square root. Sort of a weird fraction, but that's what comes out. And we can tell then from this that a hollow ball will roll down slower than a cylinder in every case. No matter its mass, no matter its radius, if they start from the same height, a cylinder will go faster than a hollow ball. And a sliding cart or block, frictionless, will go faster than anything else. This again makes sense because to move a solid cylinder in rotation, a lot of the mass is near the center. It doesn't need to move as fast. But to move a hollow sphere in rotation, a larger percentage of the mass is farther out from the axis of rotation. So it needs to move faster and has more kinetic energy taken up by the rotation. We're going to solve one more type of problem here. Again, we're going to derive a formula for the answer. And again, I'm going to choose a problem which is similar to one that we've done before, but now has a bit of rotational energy thrown in. This is called the Atwood machine with a massive pulley. In our previous approaches to the Atwood machine, which was a wheel with a string over the top and two different masses on each side. Our previous approach to this was to ignore the motion of the pulley, say that the pulley is massless, say that the pulley is an ideal pulley, or something like that. Now, we are not going to do that. We're going to say MP symbolizes the mass of the pulley, and I symbolizes the moment of inertia of the pulley. Now the radius of the pulley will actually matter. We'll let R equal the radius. Again, we'll just go through this quickly. Our goal is to let these two objects start from rest. Let MB fall a distance h. Let MA rise a distance h. And after that, to predict the final velocity of both masses. Again, we're going to approach this with conservation of energy. In the initial situation, there is no kinetic energy, and the potential energy can also be taken as 0 by setting up the origin of our vertical axis to coincide with the initial position of the masses. In the final situation, our kinetic energy comes from 1/2 ma Vf squared for the motion of mass A, 1/2 mb Vf squared for the motion of mass B, and 1/2 I omega squared F for the motion rotationally of the pulley. Putting these two things together with conservation of energy would give us 0 equals 1/2 ma plus mb plus I over r squared times Vf squared as the kinetic energy term, and then plus mg, let's see, this would be plus the final potential energy. So ma gh minus mb gh. That's the final potential energy of the system. So again, solving this equation for Vf symbolically, I would get 2gh now times the difference mb minus ma divided by sum of the masses and the moment of inertia over the radius squared. So if mb is larger, our value for h is positive, and the system gains some speed as it moves down. If we compare this to our formula for the regular Atwood machine that did not have a massive pulley, we see that we could return to that formula by just removing the part dealing with the moment of inertia. Then we would get mb minus ma over mb plus ma and return to that simpler situation. But what the pulley does here is it adds some place for kinetic energy to go. And so it increases, say, the effective mass of the system. It adds on to these inertial factors in the denominator and makes the final velocity slower. So our general summary for using rotational kinetic energy is to set up the problem as a conservation of energy problem, just as we would in previous work. But if there is a part that needs to rotate as a string pulls on it, or rotate as it rolls along the ground, then that also contributes some kinetic energy of the form 1/2 I omega squared. And this angular velocity can usually be linked up with a linear velocity divided by some radius, with a positive or negative sign that you have to figure out mostly by looking at the diagrams.